what I mean. So I scanned it in. Oops, that isn't what I want to do. I want to do this. So this is the first page. You know, it's okay. It just doesn't look like really crisp like I'm used to. So vocabulary, oftentimes part of the first part of my unit exams, I change it up from semester to semester. Sometimes this first section will be multiple choice, okay? But I was after element as a substance that consists of only one type of atom. We talked about intensive and extensive properties, and extensive are the type of property that does depend on amount. Or I said intensive, independent of amount, extensive, depends upon amount. Mole was what I was after for C, as the term used to describe Avogadro's number of particles. D, physical property is one that you know new substances are formed, i.e. physical property is you measure a characteristic and no chemical reaction has to occur. E, I was after density as the ratio of something's mass to its volume. F, molar mass, is the grams you need to set aside in order to get 1 mole of that substance, be it atoms or molecules or hockey pucks. G, the nucleus, is the center of an atom. H, isotopes are the atoms of the same element that have a different number of neutrons in their nuclei. I was after anion as the name of a negatively charged ion. Of course, electron would be the name of a negatively charged particle. J, mass number, is that is where you count the particles in the nucleus, which are protons and neutrons. That's the mass number. It's always an integer. Again, isotopes are then, since they have different number of nuclei, since isotopes have different number of nucleotides, different number of neutrons in their nucleus, then they weigh different, the same element. L, I was after proton as the subatomic particle that defines an atom, or what element an atom is. M, electron, is the subatomic particle that's not found in the nucleus. N, also electron, is of the 3 subatomic particles we talked about, the one that's basically massless. And O, I was after average atomic weight or average atomic mass. When you guys do later on in the test for silicon, take the percent abundance and the mass of each isotope and come up with a weighted average. That's the decimal number on the periodic table. Next page. So at the top there, you kind of see I was after nickel, a neutral nickel. We know it's neutral because there's no charge up there in the corner. Darn it. And I was also after a charged species. I get it. Okay. This is what I want to do. Really? That's weird. Oh, I know why that did that. One more time. So in the case of the neutral atom, nickel, when I asked various questions, especially with regard to the electrons, there were the same number of electrons outside the nucleus as there are protons inside the nucleus. So mass number for nickel, this is the upper left-hand corner. Atomic number, you could have gotten either there or just looked at the periodic table. And atomic number and number of protons are always going to be the same. And then number of neutrons, in both the case of neutral nickel atom, or that's called phosphide, the P3 minus. What you do is you take the mass number minus the number of protons to get the number of neutrons in both cases. So 32 for the nickel atom, and the number of electrons, since it is neutral, is equal to the number of protons. So the phosphide, the mass number, again, the upper right-hand corner, upper left-hand corner. Atomic number 15, since it's phosphorus, that's also the number of protons. By difference, you get the number of neutrons, And then in this case, the number of electrons is actually, it picked up 3 electrons. You can tell by the 3 minus. So it's 15 to counteract the protons in the nucleus, and an extra 3 to give it that -3 charge. So, and then down here at the bottom, remember this is the kind of question that if you have it on a grad entrance exam, you can always check it. But so there are, if you read this, and sometimes, and I was kind of in a hurry when I did this answer key, but sometimes I'll take that and kind of break it out into the 3 different isotopes: the weight, the abundance, the weight, the abundance, the weight, the abundance. It's just kind of nice. But if you read in there, you're going to come up with 3 different isotopes, and you can kind of see here in my problem how I took the mass times the percent abundance divided by 100. Mass, percent abundance divided by 100. Notice that for that last isotope that weighs 29.974 AMUs, there was no percent abundance given, so I kind of did up here, 100 minus the sum of these 2 percent abundances. So, yep, 28.09 AMUs. Answer for that one. So the next problem, the thing about rounding is here to stay. There are a few problems, and you'll hear me kind of get a little wishy-washy on them. There are just a few problems where I don't know how to round. But if it's just straightforward adding like that, then you're always going to round according to decimals. And it's fewest decimals, so that's why I put a check over the 8. Or the 8 in the tenths places in the first term. So even though the calculator displays this, this is what you got to report. Then down here, this is a type of problem where you could have left it till the end to round, or you could have rounded along the way. I gave you the mass of the object, and it happened to have nice regular shape, length, width, and height. So the density is mass divided by volume. So you could have gone ahead and, like I did, take volume and calculated it aside, round it according to 3 sig figs, okay, and then plug it in, or you could have put volume down here, and you got the same answer using the rounded or the unrounded. But again, we round to 3 significant figures. So with 3 significant figures, that's why you actually end up with 8.99 something, 8.99 in a number that's greater than 5. So that rounds up to 9.00 grams per cubic centimeter. Then down here at the bottom, this is where, those were more straightforward than this one. But if you read it, it's after mass fraction. And here I reminded you what we said mass fraction is. We're more used to dealing with mass percent, mass parts per 100, than mass fraction. Mass fraction is just relative amount per 1. Percent is relative amount per 100. So basically, they give you moles of 2 elements. Now, the thing about hydrogen and helium, the thing about helium and neon is that they weigh different. So if you're after mass fraction, you're going to have to take those moles, convert them to mass, and that's one of the things we talked about in this class. Okay, in this unit, I should say. So here is converting the number of moles of helium given to mass. Of course, this term right here came from the periodic table. Okay, and then again, we were given, with regard to neon, 0.104 moles. That's the number from the periodic table for neon. Okay, so in this situation, I have a mixture of those 2 gases. So then actually that total mass is going to go in the bottom. My component of interest is helium. Okay, so 1.48 grams of helium divided by the total 1.48 grams of helium plus 2.10 grams of neon. Okay, round it to 3 sig figs. So the next one, so in this case we're dealing with aluminum. Notice I put aluminum liquid just because I could. So the density was given in grams per cubic centimeter. Okay, and notice that, so that's what I've been saying in our review session. That's what I call the constant. The thing specific to this problem is we want to start with a particular volume of molten aluminum, 1.3 cubic meters. So right away, to use that density, I'm going to have to go from cubic meters to cubic centimeters. But then it goes on, the problem says, if you're given that volume of aluminum, what are the number of moles of protons you have? So one missing, and it's a type of equality that we have with regard to aluminum. If you have 1 mole of aluminum atoms, then because its atomic number is 13, lucky number 13, that means you have 13 moles of protons. Okay, because you have 13 protons for every one, so 13 moles for every 1 mole. So I'm going to use that in my problem too. So of course, we're going to basically go from the volume of cubic meters to cubic centimeters. See that right there. Now one of the things, and this is here to stay too, is you need to, and I'll say you instead of me because I'm pretty good at it now. You need to recognize that if we're going to convert from meters cubed to centimeters cubed, we got to go ahead and it's okay to say that there's 100 centimeters in 1 meter. That's cool. But then you got to make sure that there's a cube outside. So basically we're going to cube the 100 when we go to stick it in our calculator. So those first 2 terms will get me to volume cubic centimeters, and of course you probably recognize that next term is the density. This term right here is the molar mass. Okay, and that will get me from that volume, that will get me to moles of aluminum atoms. And then recognize that for every 1 mole of aluminum atoms I have 13 moles of protons. Okay. So the answer rounded to 2 significant figures, because that's what your volume, your 1.3 cubic meters was, is 1.5 times 10 to the 6th moles of protons. The next one, definitely, read it several times, unpack the information given. Usually, every once in a while, especially temperatures, you don't need to use. It's just like for your information because things vary at different temperatures. But usually you'll have to use these numbers. So unpacking what we're given, basically we have helium flowing at a flow rate of 35 milliliters per hour. And we're given the density of helium under those conditions, or this particular carrier gas. And then down here, I've started doing this with working my problems. Okay, the number specific to the problem is 20.0 minutes. And the question of interest is, and I don't connect those dots up there. Okay, so I want to know if you let it rip for 20.0 minutes, what grams of helium are you going to get? So then I just would go ahead and start with the thing specific to the problem. Okay, now that's time, and up here in the given information, I was given milliliters per time, but I was given milliliters per hour, not minutes. So that's why this first term is to go ahead and get my minutes to hours. Then I put in the flow rate, and then I've got volume. So one of the things about volume is I know the density, okay? And the density is in grams per liter, so I need to get from units of volume in milliliters to units of liters. So that's what that term is. Then once I have units of liters for volume, I can go ahead and plug in the density. So I got units of grams. The next one. The next one, and I do this on my exams, anything we hit hard in lab is fair game. And if this didn't ring any bells with regard to lab, you probably were not successful. Because in lab, we did this for sucrose, and I know it's hard for you to read, and it's even hard on your own sheets. But over here we have, instead of weight percent sucrose, we have weight percent copper. And this is the density of the alloy. In my answer key, if you see mixture, that's the same thing as alloy. Okay, so I just kind of doodled up there that this particular alloy has, we're going to vary the weight percent of copper, and it's going to have a different density. Okay, it's very similar to our sucrose. So you see those kind of 2 dots up there? This one right here, this dot, this first one, kind of the bottom one, is what I need to use for question number 7. Because question number 7 gives a density, And so I looked up I looked up a density on that y-axis, and you can't read it from here, of 8.62 grams per mil. And I saw where it hit the calibration curve and it came down. That's the weight percent copper. Only then could I work the problem. And it had a similar situation with regard to question 8. So it is possible that there are kind of maybe a few different answers out there when students work this. But I got 76%. Now that's 76% copper. That means for that particular sample of interest for question number 7, I have 76 grams of copper in 100 grams of alloy, or 100 grams of mixture. Okay, and it goes ahead now, specific to the problem is that 25 grams of copper. And I'm after moles of zinc. Okay, so you see down here, if I start with the 25 grams of copper, now you could have done this a couple different ways, but I went ahead and if it's 76% copper in that sample, and it's only got 2 things, in 100 grams of that sample, can you see where it's got, what you see here, it's got 24 grams of zinc for every 76 grams of copper. That's what that second term is. You could have either done it this way or done it like 100 grams of alloy over 74 grams of copper, and then the next one would have been the 24 grams of zinc over 100 grams of alloy. Either way. So this will get me to grams of zinc given that density and the corresponding weight percent of copper. Once we have grams of zinc, you probably recognize that last term is just the molar mass of zinc. Okay? So then down here at the bottom, again, given the weight percent, and in this case, this is what you'd use for number 8. Okay, so this is the density. It corresponds to, you can see a higher percent of copper, and I got 88%. Again, it's kind of roughing it. Okay, so then working the problem with that in mind, we're supposed to say, now I start out this number I didn't use is the number I'm going to start with. So basically, you can kind of see here, mapping it out with kind of a blank in between these arrows. I want to go from 5.00 moles of copper to question mark volume of the alloy or the mixture. So if I plug in my moles of copper, I know I got mass of copper, relatively speaking, so my next term is to get it to mass of copper using the molar mass of copper. Once I get mass of copper, then I can get mass of alloy by recognizing it's 88% copper. That's this, 88 grams of copper per 100 grams of alloy or mixture. Then I can plug in the last, so that's weight percent, and the last term is density. Once you have grams of the alloy or grams of the mixture, you can go ahead and use density, but notice that you're going to use the flipped version because you want grams to cancel. You'll be left with milliliters. And last but not least on this roller coaster of your first unit exam were some questions here. Picking from that list of 8 elements, you only had to pick one if there was a possibility of more than one. But the nonmetals, remember, look for the JAG and set anything up there in that little kind of upside down triangle over there on the right. Question... nonmetal? I don't think uranium belongs there. Who did this answer key? I don't think anybody put uranium. That's strange. Okay. Oh, I know. I should have put chlorine. I'll change my answer key maybe if I think about it. So oxygen, xenon, and chlorine are all over there. The next one, transition element, that would be the group B elements. Notice that silver and gold fit that bill, but I also would have taken uranium, which goes down later as an inner transition element. Question C. Now remember, the period numbers are over here, on the periodic table I gave you. And the period, this is a period, and which period is right over here. So period number 2, oxygen is the only one. Halogens, those are 7A elements, and chlorine's the only one that fits that bill. E, alkali metal, those are 1A elements, sodium. F, noble gases, remember that's rare gases or inert gases, that's 8A, that's clear over there at the right. And then an intertransition element, that would be, the only one is uranium.